Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at planes. So a plane is the set of all points obtained by starting at some point A and moving in all combinations of two non-parallel vectors. A plane has an equation and it can be constructed according to this. So what exactly does that mean? Well, A is the position vector of some point. So if we want to construct a plane, we start with a point and then we take two vectors here as long as they're not parallel and we look at all the possible, these are called linear combinations of them, and add them to A. The result is we end up with a two-dimensional space like this. Now planes always have a normal vector which we denote n. That's perpendicular to the plane. It's in 3 dimensions, so it's going up relative to the plane. The normal vector is not unique. So if n is a normal vector, any scalar multiple of n is also a normal vector. But for our purposes, we're not necessarily constructing planes. We want to define planes mathematically through equations. So the way we do that is with this equation here, which is called the vector equation. So how we get that, we have some vector A that we start with. The plane is the set of all vectors R that satisfy this equation here, where n is the normal vector. So hopefully this will be a bit clearer when we do an example. So here we have 3 points in 3 dimensions. As long as they're not collinear, there will be a unique plane that contains them all. What we need to be able to do is find the equation of such a unique plane, and we will find both its vector and its Cartesian equations. So to start with, we are going to label the points capital A, B, and C. Each is associated with a vector. So vector A is just going to be 4i plus 3j plus 2k, and similarly for B and C. Now the plane of which we speak doesn't contain all of these vectors, it contains their endpoints. But what we do know is it will also contain the endpoints of the difference of these vectors. This means that the plane will contain the endpoints of the vectors b minus a and also c minus a. So these vectors, if they don't lie in the plane, will be parallel to the plane. So we can use them to find the normal vector. We can do this as long as they're not scalar multiples of each other, which in this case they're not. So to find a vector that's orthogonal to these two direction vectors, we simply calculate their cross product. So for this orthogonal vector, the I component will be negative 4 times negative 2, subtract negative 2 times negative 2. That will give the I component of the vector. The j component of the vector is negative 2 times negative 2, subtract negative 2 times negative 4. And then the k component will be negative 2 times negative 2, subtract negative 4 times negative 4. So that gives us a normal vector of 4i plus 4j minus 12k. Now, because any scalar multiple of this will also be a normal vector, we could divide these by 4 just to make life simpler for us. So I plus j minus 3k, see I've divided each component here by 4. That gives us a possible normal vector. So as we said on the previous slide, the vector equation is of the form r minus a dot n equals 0. We want the dot product to be 0 because all the vectors on the plane need to be orthogonal to the normal vector n. For a, we can choose any of the vectors with which we started. We may as well just choose this one here, a. So we have r minus our vector a, which was 4i plus 3j plus 2k, dot product with n, which was I plus j minus 3k. That has to equal 0. And this completely defines the plane that contains these points. Basically, what you can do, if you want to see whether or not a point lies on this plane, you can substitute its position vector for r and see if this gives you a true statement. All right, let's now use this to get the Cartesian equation. So to get the Cartesian equation from the vector equation, the Cartesian equation is the one with the x, y's, and z. We're just going to let r be xi plus yj plus zk, and we're going to substitute it into here. So what would be r minus this vector? Well, it would simply be x minus 4. We're subtracting each component one by one, x minus 4i. Then we'll subtract the y components, so we have y minus 3j. And then we'll subtract the z components, so we have z minus 2k. So when we use the dot product of this with I plus j minus 3k, we should get 0. So if you expand this out with the dot product, we multiply the x components together, so it's just 1 times x minus 4 plus 1 times y minus 3 minus 3, lots of z minus 2 is equal to 0. So now all you need to do is expand any brackets and simplify. We will get x plus y minus 3z, and then negative 4 minus 3, subtract 3 times negative 2, that gives us negative 1. So the plane of which we are speaking contains all of the points x, y, and z that satisfy this equation here. So the result will be a 2D object, a 2D space amongst the three-dimensional axis. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.